So from an earlier discussion, we learned that the slope on a velocity versus time graph tells us the acceleration of the object. But there's more that we can get from that type of graph. And today we'll learn how to find displacement and also distance traveled from that graph. To begin, let's look at a problem where we know the answer so that we can see how this method works. If an object's going at a constant speed of 5 meters per second, that means it travels 5 meters every second. So after 7 seconds, it will have traveled 35 meters. We can see that on a graph as well. This graph shows the object's motion with a horizontal line at the 5 meter per second mark. Now we are only interested in the first 7 seconds, so let's cut the graph off at that point. When we do this, we see a shape form, a rectangle, that's bounded or bordered by the red line and then this dotted line that we've put in. That's the important part, the area on this sort of graph. Take a look at what the area comes out to be. 5 along the height and 7 along the base. So the area is 35. And looking at units, 5 meters per second times 7 seconds, again 35 meters. Another way for us to answer the question. So this will allow us to handle much more complex situations where the speed either changes in sudden bursts or if it has a gradual acceleration. The key idea is that the area on a velocity versus time graph can tell us the displacement and also the distance traveled. We'll see in a few minutes the difference between those two things. Here's a car that has very distinct values of velocity at different times. It's very quickly changing its speed. If we break this shape into simpler shapes, we'll be able to determine the area between the red line and the axis. So now we have 4 rectangles that we need to consider. And just looking at a very simple base times height, 16 times 2 is 32, 12 times 3 is 36, 6 times 2 is 12 meters, and then 4 times 1. And then to find the total distance traveled, or the total displacement, we would just need to add all of those values up to get 84 meters. Now in this case, the distance traveled and the displacement are the same thing, because this object only moves in the positive direction. All of the velocities are positive, none are negative. But this object starts off in the positive direction, traveling 16 meters per second, stops for a second, then travels at 8 meters per second, stops for a second, and then actually reverses and begins going backward. When we go ahead and split this into simpler shapes so that we can calculate the area, we get these values. Now we can use those to determine 2 different things. We can just simply add up all the values, and that gives us the distance, or we can take into account that the last 2 represent movement in the opposite direction, the negative direction. And we can use that to determine the displacement. So the distance traveled is 100 meters, just adding all the values. The displacement, we consider the first 32 meters and the 16 meters to be in the forward direction. And then we subtract 20, subtract 32, and we see that we actually end up 4 meters behind the starting point. The answer comes out to be -4. So that's what happens if our object suddenly jumps from one speed to another. But a more realistic situation is an object like this truck that gradually speeds up with a very consistent acceleration. Let's take a look at the graph that fits this truck. You can see from our graph that it ranges from 0 to 24 meters per second, and that change requires 8 seconds. That's what the problem is describing. And assuming that the acceleration is constant, we would have this nice straight line connecting them. That represents the acceleration if we were to find the slope, but we're interested in how far the truck travels. So we need to look at the area that's formed by these various lines. To find the area of a triangle, of course, we need to take 1/2 times the base times the height. And so in this case, that would mean the height of 24 meters per second, the base of 8 seconds, and then that comes out to be 96 meters. So no matter what the shape is, the shape will tell us, the area of that shape will tell us how far the object has traveled. And if it's above the axis, it means the object is moving forward. If it's below the axis, the object moves in reverse. Now there's a few more examples that we're going to go through. You may want to follow along on the sheet that you were given in class and see if you can work ahead. So maybe stop the video, try to determine the displacement or the distance, and then check your work with the solution on the video. To answer this question, determining the displacement from 0 to 6 seconds, I would look for 3 shapes. This is how I would divide this area into triangles and rectangles. Now if you know area of a trapezoid, you can certainly use that here. I just feel more comfortable with rectangles and triangles. So I would use the scales on the velocity axis and the time axis, and I would find that the areas are 10 meters, 30 meters, and 5 meters, so that the total displacement is 45 meters. Now again, if the question had asked about distance traveled, that would also be 45 meters, because this object only goes in the positive direction. All values of v are positive on this graph. Let's take a look at this graph. We have to be careful sometimes. We don't always use the entire graph. This question only asks for the displacement from 0 to 10 seconds. So we need to make sure we cut the graph off at that point, at that time. And then we look at the remaining shape and determine what shapes will be easy for us to work with. And this is what I would choose. Again, there are a couple different ways you could set this up, but I would work with this triangle and this rectangle, making sure I use the scale on the axes. We find that the rectangle is 100 meters, and the purple triangle represents 20 meters. So our displacement would be 120 meters. Again, this is also the distance traveled, because this object only moves in the positive direction. All right, let's take a look at this last example. And again, notice how the graph drops below the axis, like it did a couple of times ago, but now with a slanted line, with acceleration. So we want to make sure that we choose our areas carefully. This ends up being a rectangle and 2 triangles. And what's nice is the 2 triangles actually have the same area. And so when we find the displacement, those 2 areas, those 2 20-meter distances, they can just be sort of canceled out because you add one and then subtract one. Displacement is only 40 meters. But the distance traveled would have to take into account all of these distances sort of as the absolute value, as the positive value. And so the total distance traveled would be 80 meters.